For centuries, humans have looked up at the night sky and wondered if the stars are reachable. Today, science is telling us that the dream of traveling not just to nearby planets, but to entirely different galaxies may one day be possible. The universe is vast beyond comprehension, yet physics gives us clues, hints of propulsion systems, energy sources, and cosmic shortcuts that could turn intergalactic travel from fantasy into reality. What once belonged to science fiction is slowly becoming an engineering question constrained only by the laws of the cosmos and our imagination. The universe is unimaginably vast, stretching across distances that defy everyday comprehension. When we speak of traveling to other galaxies, we are contemplating journeys that span millions of light years, scales so immense that human intuition struggles to grasp them. A single light year, the distance light travels in 1 year, is already nearly 6 trillion miles. And yet galaxies are separated by millions of such units. The Andromeda Galaxy, our nearest galactic neighbor, lies approximately 2.5 million light years away. This means that even traveling at the speed of light, a journey that would take 2.5 million years, the scale of these distances transforms what might seem like a straightforward expedition into a cosmic odyssey, demanding solutions that challenge our current understanding of physics and engineering. Traditional propulsion methods, rooted in chemical rockets or even nuclear propulsion, are insufficient. They are simply too slow, and the energy demands grow to astronomical levels. To conceptualize intergalactic travel, one must first recalibrate the human mind to think in terms of vast cosmic distances, where time, energy, and motion interact on scales far beyond earthly experience. To imagine traversing these distances, one must also account for the relativistic constraints imposed by Einstein's theories. According to the special theory of relativity, as an object approaches the speed of light, its mass effectively increases, requiring exponentially more energy to continue accelerating. This means that conventional propulsion methods face diminishing returns as we attempt to approach the ultimate cosmic speed limit. Even if we harnessed all the energy available on Earth, reaching even a fraction of the speed of light would take decades or centuries, let alone crossing millions of light years. Here, physics both limits and guides us. While it constrains us within certain parameters, it also suggests possibilities that are otherwise invisible. Concepts such as time dilation, where time effectively slows down for travelers moving near light speed, offer a potential solution for intergenerational voyages, although millions of years might pass in the galaxy outside. For those traveling at relativistic speeds, only decades might elapse. This subtle interplay between velocity, time, and distance hints at how human ingenuity might one day navigate the vastness of space. The first challenge, therefore, is the scale itself. Every calculation, every plan, must begin with an acknowledgement of the enormity of the cosmos. Distances, travel times, and the sheer number of unknown variables dwarf any Earth-based engineering problem. Galaxies are not merely far away. They are dynamic, moving entities influenced by gravity, dark matter, and cosmic expansion. Any intergalactic journey must account for these motions. Stars orbit the centers of their galaxies. Galaxies themselves are moving relative to one another, and the fabric of space is constantly stretching due to cosmic expansion. Thus, plotting a trajectory to another galaxy is not simply a matter of drawing a straight line. It requires mapping a constantly evolving three-dimensional lattice of celestial bodies, predicting the position of stars and planetary systems millions of years into the future. In this sense, traveling between galaxies is not merely a feat of propulsion, but an exercise in cosmic navigation and predictive physics, where success depends on understanding motion on incomprehensible scales. To tackle these challenges, physicists have explored faster-than-light concepts which, while speculative, are grounded in theoretical physics rather than fantasy. Wormholes, for instance, emerge naturally from solutions to Einstein's equations of general relativity. They represent hypothetical tunnels through the fabric of space-time, connecting distant regions of the universe in such a way that the effective travel distance is drastically reduced. Instead of moving across millions of light years, a traveler could, in principle, enter one mouth of a wormhole and exit near the target galaxy instantaneously. Wormholes are not magic. They are permitted by the mathematics of curves. Space-time though their physical existence remains unproven. The primary challenges involve stabilization, preventing collapse, and shielding travelers from extreme gravitational forces. Exotic matter with negative energy density might be required to keep a wormhole open, a concept that stretches our understanding of energy and matter, but does not violate any known physical law. This theoretical framework offers a glimpse into a universe where intergalactic travel could be conceptually feasible, even if the engineering hurdles are currently insurmountable. Warp drives constitute another approach to faster-than-light travel, relying on the flexibility of space-time itself, rather than the brute acceleration of a spacecraft. The idea is to contract space in front of the vehicle and expand it behind, effectively moving a bubble of space rather than the ship through space. Inside this bubble, the ship remains at rest relative to its local space, avoiding relativistic penalties like time dilation or infinite mass increase. The Alcubierre drive, proposed in the 1990s, is a mathematical solution to Einstein's field equations illustrating this possibility. While the energy requirements are initially daunting, later refinements suggest that with sufficient control of exotic energy and space-time curvature, such a drive could, in principle, move a spacecraft across galactic distances without violating the speed of light locally. The physics is rigorous, the math is consistent, and while the technology remains speculative, it frames intergalactic travel as a problem to be solved, not a fantasy to be dismissed. Both wormholes and warp drives highlight a crucial principle: the universe does not forbid intergalactic travel, it only imposes rules. These rules, embedded in the fabric of space, time, and energy, define the boundaries of possibility. Unlike a mythical universe where distances are arbitrary and motion is unconstrained, our cosmos has measurable, predictable laws. By studying them, scientists can identify shortcuts, optimizations, and methods that exploit the underlying structure of reality. This represents a shift in mindset. Early humans viewed the ocean as an obstacle, later they understood its physics, currents, and wind patterns, turning it into a highway for exploration. Similarly, understanding the physics of space-time may transform the intergalactic void from an insurmountable barrier into a navigable medium where clever engineering can bend the rules without breaking them. Energy requirements are intrinsically linked to these concepts. To accelerate a massive spacecraft to near light speeds, or to stabilize a wormhole, or to warp space-time, demands energy on scales that challenge imagination. We are talking about harnessing the output of entire stars, concentrating it, and converting it into forms usable for propulsion. Physics tells us that energy and mass are interchangeable and that the conservation laws remain inviolate. Yet within these laws, enormous room exists for creativity. Advanced civilizations, perhaps millions of years ahead of us, might have learned to manipulate energy with precision far beyond current human capability. Studying these theoretical possibilities not only informs our ambitions, but frames the limits within which our own technological evolution must operate. Energy is the currency of intergalactic travel, and mastering it is the first step toward traversing the void. In summary, contemplating travel to other galaxies requires a mind attuned to both the vastness of space and the subtleties of relativistic physics. Distances are enormous, galaxies are in motion, and conventional propulsion methods are insufficient. Yet physics offers conceptual solutions, wormholes, warp drives, and relativistic trajectory that do not violate known laws, only challenge our current engineering limits. Energy requirements, navigation, and human endurance all demand radical new approaches, but the universe itself does not forbid such journeys. The task is not merely to dream, but to calculate, experiment, and innovate within the rigorous boundaries of cosmic law. By doing so, humanity takes the first step from wondering about other galaxies to understanding how one day we might actually reach them. The energy requirements for intergalactic travel are staggering, stretching the limits of imagination and engineering. To understand the magnitude, one must first recognize that accelerating any mass to relativistic speed, fractions of the speed of light, requires energy that grows exponentially as velocity increases. The closer a spacecraft approaches the speed of light, the more energy is required, not linearly, but according to the relativistic formulas. derived from Einstein's special relativity. For even a small spacecraft, achieving just 10% of light speed would consume energy comparable to the total annual energy output of the entire planet. To reach significant fractions of light speed sufficient for intergalactic journeys, the required energy approaches the output of entire stars or even small galaxies. This is not a speculative exaggeration, it is a direct consequence of the physics that governs mass, velocity, and energy. Every plan for traveling between galaxies must confront this stark reality. Yet within this constraint lies an opportunity for ingenuity. One pathway involves harnessing antimatter, the ultimate energy-dense fuel known to physics. When matter meets antimatter, they annihilate completely, releasing energy according to the famous equation E equal to mc2. The energy yield is unparalleled orders of magnitude higher than chemical or nuclear reactions. With just a few grams of antimatter, one could, in principle, propel a spacecraft to relativistic speeds. The challenge lies in production, storage, and controlled release. Antimatter does not exist freely in nature in sufficient quantities. It must be manufactured using particle accelerators and carefully stored in magnetic bottles to prevent premature annihilation. While current technology produces only minute amounts, the laws of physics impose no fundamental limit on scale. If future civilizations learn to produce and manipulate antimatter efficiently, intergalactic propulsion could become feasible. It represents not a violation of natural law, but a meticulous application of it. Fusion power offers another route, leveraging the same process that powers stars. By fusing light nuclei, such as hydrogen isotopes, enormous energy is released in the form of kinetic energy of reaction products. Fusion propulsion systems, such as the theoretical fusion pulse designs, could provide sustained thrust over decades or centuries, gradually accelerating a spacecraft to high velocities. Unlike chemical rockets, which exhaust fuel rapidly, fusion allows for long duration acceleration, a crucial factor for crossing millions of light years. Physics dictates the parameters: reaction rates, energy density, and containment, but within those constraints, engineers can optimize design, channeling energy efficiently into motion. Coupled with advances in superconducting materials, magnetic confinement, and radiation shielding, fusion propulsion becomes more than theory. It becomes a tangible approach to navigating the cosmos. Solar sails present a complementary method, exploiting the momentum of photons rather than the energy of reaction mass. Though the force from individual photons is minuscule, over vast distances, continuous exposure can accelerate a craft to significant fractions of light speed. Physics governs the interaction between light and matter, dictating reflectivity, surface area, and orientation. Advanced materials, perhaps incorporating graphene or metamaterials, can maximize photon pressure while minimizing mass. A spacecraft propelled by light requires no fuel in the conventional sense, relying instead on the radiation naturally available from stars or from directed energy sources generated by future civilizations. While acceleration is gradual, the advantage lies in sustainability and simplicity. Over centuries, a solar sail could traverse interstellar and even intergalactic space, requiring only maintenance of orientation and structural integrity. Life support for multi-generational voyages presents a problem of equal complexity. Crossing intergalactic distances would likely take centuries, even with near light speed travel, necessitating systems that support human life over extended periods without resupply. Physics defines the constraints. Energy must be conserved, matter must be recycled efficiently, and radiation shielding must protect inhabitants from cosmic rays and high-energy particles. Closed ecological systems, artificial gravity, and advanced hydroponics are all essential. A spacecraft becomes a self-contained habitat, a miniature biosphere in which every joule of energy and every molecule of matter is continuously cycled. Any inefficiency compounds over decades or centuries, potentially endangering the mission. Engineering such habitats requires a profound understanding of thermodynamics, fluid dynamics, and radiation physics, as well as robust systems capable of self-repair and adaptation. Radiation shielding is particularly critical. The universe is filled with high-energy particles, cosmic rays, gamma rays, and solar flares that can damage DNA and electronics. Physics allows us to calculate exposure rates, attenuation requirements, and material effectiveness. Shielding may involve layered composites, magnetic fields that deflect charged particles, or even water and hydrogen-rich substances that absorb radiation efficiently. For multi-generational crews, exposure limits are strict, and failure is not an option, protecting human life over centuries in the harsh environment of intergalactic space demand. Innovations that integrate physics, biology, and materials science seamlessly. Autonomy and redundancy become fundamental principles in life support and propulsion. Humans cannot oversee every process continuously over decades. Systems must operate independently, monitor themselves, and respond to unforeseen challenges. Artificial intelligence plays a key role analyzing data from thousands of sensors, predicting failures, and executing corrections in real time. Physics defines the boundaries. Energy cannot be created or destroyed, and mass and momentum must be conserved. Within these laws, autonomous systems can manage thousands of interdependent variables, ensuring that acceleration, life support, and navigation remain within safe parameters. The spacecraft becomes both home and guardian, a complex integration of machines and humans, guided by the immutable rules of the cosmos. Social and psychological factors are intertwined with these physical constraints. Humans living aboard multi-generational vessels must maintain health, morale, and cooperation over centuries. Physics does not directly dictate psychology, but it sets the environment in which human life unfolds. Gravity or artificial gravity, radiation levels, energy availability, and the integrity of habitats all influence well-being. The design of communal spaces, rotational schedules, and educational systems must account for these variables to prevent deterioration over time. Every solution, from structural reinforcement to energy allocation, must balance human needs with physical feasibility demonstrated. That intergalactic travel is not merely a technical challenge, but a holistic one where biology, sociology, and physics converge. Ultimately, the energy requirements and life support systems for intergalactic travel are not insurmountable in principle, but they demand mastery over forces, matter, and radiation at scales unprecedented in human experience. Antimatter, fusion, and photon propulsion illustrate that physics provides pathways, not impossibilities. Closed ecological systems and radiation shielding show that survival over centuries is theoretically achievable when laws of energy, mass, and momentum are respected. The challenge is staggering, but it is framed by the immutable, predictable laws of nature. Intergalactic travel is less about defying physics and more about understanding and harnessing it, turning seemingly insurmountable obstacles into engineering problems solvable with insight, precision, and imagination. The physics of propulsion lies at the very heart of intergalactic travel, dictating what is possible and what remains beyond reach. Traditional chemical rockets, limited by the energy density of chemical bonds, are insufficient for journeys spanning millions of light years. To cross such unimaginable distances, we must look to the most extreme and energy-dense propulsion methods that physics allows. Antimatter engines represent one such possibility. In these systems, the annihilation of matter with its antimatter counterpart converts mass entirely into energy, yielding orders of magnitude more thrust than conventional fuel. A gram of antimatter interacting with a gram of matter produces an energy release equivalent to the detonation of tens of thousands of tons of TNT. Harnessing this energy, channeling it safely, and converting it into directional thrust are monumental engineering challenges, yet they remain theoretically achievable within the constraints of known physics. Antimatter engines offer a pathway to relativistic speeds, allowing spacecraft to traverse vast interstellar and intergalactic distances within humanly conceivable timeframes. Fusion propulsion provides another avenue, relying on the same process that powers stars. By fusing light nuclei, such as isotopes of hydrogen, enormous energy is released. This energy can be converted into thrust through a variety of mechanisms: directed plasma jet, magnetic confinement, or controlled explosions in the case of fusion pulse propulsion. Fusion offers the advantage of sustained acceleration, critical for journeys lasting decades or even centuries. Unlike chemical rockets, which burn quickly and exhaust fuel, a fusion-powered ship could maintain thrust for extended periods, gradually increasing velocity to significant fractions of the speed of light. The challenges here are considerable, containing plasma at millions of degrees, managing heat dissipation, and protecting the vessel and crew from radiation. Yet each obstacle is a matter of engineering within the immutable laws of thermodynamics, electromagnetism, and nuclear physics. The promise of fusion propulsion lies in its combination of efficiency, longevity, and scalability, potentially enabling humanity to bridge the cosmic gulf between galaxies. Beyond these high-energy propulsion methods, solar sails illustrate how physics allows for subtle yet profound alternatives. Utilizing the momentum of photons from stars or directed laser rays, spacecraft can accelerate without traditional fuel. The force from individual photons is minuscule, yet over long durations, continuous exposure imparts significant velocity. The design of a solar sail requires careful consideration of reflectivity, surface area, and mass, all governed by classical mechanics and the principles of momentum transfer. Advanced materials, such as ultralight composites or graphene-based fabrics, maximize thrust, while minimizing mass, enabling a spacecraft to gradually achieve relativistic speeds. While acceleration is slow, the energy requirements are dramatically reduced, and maintenance becomes less complex compared to high-thrust engines. Solar sails demonstrate that intergalactic propulsion does not necessarily demand explosive energy output. With patience and precision, light itself can become a vehicle propelling humanity across the cosmos. Navigating the hazards of deep space is inseparable from propulsion, as every particle and photon in intergalactic space presents a potential threat. Even tiny grains of interstellar dust traveling at relativistic speeds carry tremendous kinetic energy, capable of puncturing spacecraft hulls or damaging delicate instruments. Radiation from cosmic rays, gamma bursts, and energetic particles from nearby stars further complicates long-distance travel. Physics allows us to calculate fluxes, attenuation lengths, and shielding effectiveness, guiding the design of protective measures. Magnetic fields, for instance, can deflect charged particles, while layered materials absorb high-energy impacts. These protective systems, integrated with propulsion, create a spacecraft capable of withstanding the relentless hazards of intergalactic space. The challenge is not merely survival, but maintaining operational efficiency and energy balance. Over centuries-long voyages, where every joule and every gram of matter is precious, the interaction between propulsion and life support systems is profound. High-energy engines generate radiation, heat, and electromagnetic fields that can affect both humans and electronic systems. Shielding must be integrated into the spacecraft structure without compromising mass efficiency or thrust performance. Thermal management becomes a critical component. Reactors must expel excess heat, radiation must be absorbed or diverted, and living areas must maintain stable temperatures for multi-generational crews. Physics dictates the limits. Heat transfer, material strength, and energy conservation are immutable, yet within these constraints, engineers can innovate. The spacecraft becomes a delicate balance of propulsion, protection, and habitat, a microcosm of interstellar ecology where energy and matter circulate harmoniously. The efficiency of propulsion is inseparable from the sustainability of life, creating a system where every function supports the others. Autonomy and artificial intelligence are essential companions to propulsion in intergalactic travel. Human reaction times are inadequate to navigate a spacecraft traveling near the speed of light through regions filled with radiation, debris, and gravitational anomalies. Autonomous systems continuously analyze data from sensors, predict potential collisions, and adjust trajectory in real time. Physics provides the framework, conservation of momentum, orbital mechanics, and energy transfer determine possible paths, while algorithms compute optimal courses within those laws. AI acts as an intermediary between raw physical laws and practical operation, translating the immutable rules of motion into actionable adjustments for the spacecraft. In this way, propulsion is not just mechanical, it is computational, integrated with decision-making systems that anticipate challenges before they manifest, ensuring safety and efficiency over centuries-long journeys. Scaling propulsion for intergalactic travel also necessitates reconsideration of structural design. Engines capable of producing immense thrust introduce forces that propagate throughout the spacecraft, stressing the hull, decks, and internal systems. Vibration, recoil, and thermal expansion must all be managed meticulously. Physics informs engineers about material limits, resonance frequencies, and stress distribution. By employing advanced composites, adaptive structural elements, and real-time monitoring, spacecraft can maintain integrity under continuous acceleration. This integration of propulsion and structure reflects a deeper principle. Intergalactic travel is not merely about speed, but about harmony between energy, mass, and motion. Every thrust vector, Every pulse of energy interacts with the vessel as a complex physical system, requiring precise understanding and control. Finally, the combination of advanced propulsion and hazard mitigation transforms our conception of time and distance. By approaching relativistic speeds, time dilation becomes significant centuries. Outside the spacecraft may pass, while only decades elapse for those aboard. Physics allows us to exploit this effect, effectively shortening the subjective duration of intergalactic travel. Meanwhile, shielding, navigation, and autonomous control ensure that the voyage is survivable and efficient. The integration of energy-dense propulsion, protective systems, and intelligent computation exemplify the application of fundamental physical laws toward a grand human goal, reaching other galaxies. It demonstrates that intergalactic travel is not simply a question of imagination, but of mastering energy, motion, and matter on cosmic scales, transforming what once seemed impossible into a problem of physics to be solved, engineered, and ultimately realized. Artificial intelligence and autonomous systems are not mere accessories to intergalactic travel. They are fundamental to its feasibility. When a spacecraft accelerates to fractions of the speed of light, the environment outside becomes increasingly hostile. Cosmic rays, micrometeoroids, gravitational anomalies, and intense radiation fields present continuous threats that human reaction times alone cannot manage. AI systems integrated deeply into the spacecraft's architecture monitor thousands of variables in real time, detecting hazards, predicting trajectories, and executing corrective maneuvers long before any human could respond. These systems operate within the immutable laws of physics, calculating momentum transfers, force distribution, and energy efficiency, but they do so with precision and speed far beyond human capability. They act as the nervous system of the spacecraft, continuously interpreting data, optimizing routes, and maintaining the delicate balance between propulsion, navigation, and life support. Without this level of intelligence, intergalactic voyages spanning centuries would be unmanageable. The combination of physics and computation transforms perilous space into a navigable medium. Autonomous decision-making also extends to energy and resource management. Life support, propulsion, and shielding systems consume energy in a complex interplay that must remain balanced over decades or centuries. AI algorithms calculate optimal energy allocation, prioritizing critical functions while conserving resources, ensuring that propulsion thrust, thermal regulation, and environmental controls operate efficiently. Physics sets the boundaries. Energy cannot be created from nothing, matter cannot be destroyed arbitrarily, and momentum must be conserved in all maneuvers. Within these boundaries, intelligent systems maximize efficiency, creating a spacecraft that is self-sustaining and adaptive. Predictive algorithms also monitor system degradation, performing preventative maintenance or adjusting operational parameters to avoid catastrophic failures. In this sense, AI functions not only as a navigator but as a steward, maintaining the long-term viability of the mission against the relentless entropy of the universe. The second element critical for intergalactic travel is navigating cosmic hazards. The vast voids between galaxies are not empty, they are filled with particles, radiation, and occasional rogue bodies moving at extreme velocities. Even submillimeter particles can deliver immense kinetic energy to a spacecraft traveling relativistic speeds capable of penetrating hulls or damaging sensitive instruments. Physics provides the formulas to calculate impact energies, shielding effectiveness, and deflection strategies. Layered materials, magnetic fields, and active deflection systems can mitigate these dangers, but their effectiveness requires continuous monitoring and precise adjustment. Here, autonomous systems again play a pivotal role, dynamically adapting to changing conditions and executing protective measures in real time. Navigation is not simply a matter of plotting a course, it is a continuous process of prediction, observation, and response, a symphony of motion guided by physical laws and computational intelligence. Radiation hazards further underscore the necessity of integrating AI with physical systems. Cosmic rays, gamma bursts, and high-energy particles pose significant threats to both electronics and human occupants. Shielding must be calculated meticulously to reduce exposure without adding prohibitive mass. Magnetic fields can deflect charged particles, water and hydrogen-rich materials can absorb energy, and structural design can route vulnerable areas away from high-risk zones. Autonomous monitoring ensures that these protective measures adapt to the spacecraft's trajectory, energy state, and external conditions. Radiation is relentless and unavoidable, but physics gives us the tools to understand its behavior and optimize defenses. Coupled with AI, these defenses become dynamic, adjusting in real time to the unpredictable environment of intergalactic space. Life support is another domain where physics, autonomy, and intelligence converge. Multi-generational crews require closed ecological systems capable of recycling air, water, and nutrients indefinitely. Fluid dynamics governs circulation of water and gases. Thermodynamics determines heat balance. And materials science ensures containment of essential resources. Autonomous systems regulate these processes, adjusting flows, pressure, and temperature to maintain optimal conditions. Sensors detect deviations in composition or contamination, triggering corrective actions before minor issues escalate. Physics ensures that conservation laws are respected, while AI ensures that human needs are met over centuries-long voyages. In effect, the spacecraft becomes an intelligent, adaptive ecosystem where every physical law is harnessed to sustain life against the unforgiving vacuum of space. The psychological and social dimensions of intergalactic travel are intertwined with physical and computational systems. Even with perfect propulsion, shielding, and life support, maintaining human health, morale, and cohesion over generations requires thoughtful design. Artificial gravity, radiation shielding, energy allocation, and habitat layout all influence well-being. Physics dictates the environment, but AI and automation shape the experience, creating adaptive lighting, climate control, and habitat rotation systems to optimize comfort and productivity. Social structures may be managed by predictive modeling, ensuring stability and continuity over centuries. The spacecraft is thus simultaneously a vehicle, a habitat, and a social organism. Its design informed by physics, technology, and an understanding of human behavior. Advanced propulsion, hazard mitigation, and autonomous systems together redefine our conception of time and distance. Traveling at near light speeds, relativistic effects like time dilation become significant. Centuries may pass in the external universe while only decades elapse. For those aboard, a direct consequence of Einstein's relativity. Physics provides the framework for understanding these phenomena, while AI and autonomous systems manage the practical implications, coordinating energy, navigation, and life support in sync with the spacecraft's relativistic journey. In this way, intergalactic travel transforms from an abstract dream into a plausible, if extraordinarily complex, engineering challenge. It becomes a carefully orchestrated interplay of energy, motion, protection, and intelligence, all governed by immutable cosmic laws. Ultimately, intergalactic travel reshapes humanity's understanding of civilization and destiny. The integration of propulsion, life support, hazard management, and artificial intelligence allows humans to extend their reach beyond the confines of a single galaxy, opening new frontiers for exploration, settlement, and discovery. Physics remains the ultimate arbiter, defining what is possible and constraining what is not, but within those boundaries, ingenuity, computation, and engineering make the universe navigable. The potential for encountering new forms of life, understanding cosmic evolution, and establishing intergalactic societies challenges our imagination and philosophical perspective. Intergalactic travel is not merely a technological goal, it is a transformation of human perspective, a journey in which physics, intelligence, and creativity converge to extend the reach of civilization across millions of light years, making the cosmos itself a canvas for human ambition and understanding. As we contemplate the possibility of traveling to other galaxies, it becomes clear that the journey is not merely a question of imagination, it is a challenge defined by the immutable laws of physics, energy, and motion. From the staggering distances between galaxies to the extreme energy requirements, from advanced propulsion systems to autonomous life support and navigation, every aspect of intergalactic travel demands mastery of nature's rules. Yet within these constraints lies the opportunity for human ingenuity, creativity, and courage to transform what once seemed impossible into a tangible goal. The integration of artificial intelligence, intelligence systems, and innovative engineering allows humanity to envision a future where the stars are within reach, where civilizations may one day explore beyond their own galaxies, and where the universe itself becomes a stage for discovery and growth. Thank you for joining this journey, for exploring the cosmos with curiosity, for daring to imagine what lies beyond the limits of our current experience. Your interest and engagement help keep the vision of intergalactic exploration alive.